What a pleasure. I'll get right into it. I have an argument to make to you today, which is that the size of the sediment particles that are produced on hill slopes and delivered to rivers are key to landscape evolution. And this phenomenon of production of grain sizes that vary is something that people have not investigated systematically, despite really centuries of the opportunity to do so. And I think partly was because people made assumptions about they were all the same everywhere, or maybe they didn't matter, or maybe it was just too hard. But what I want to leave you with is the idea that this is an exciting and tractable area of investigation that really matters, okay? And so this picture sort of summarizes what happens. This is the Salmon River in Idaho, and there's a bedrock slope that is fractured, it's weathering, it produces particles, free particles are born, they land on this slope, a talus slope, and they make their way to the river. And when they reach the river, they influence pretty much everything that happens there. And this is, of course, just one of innumerable possible settings like this, but I really like this one because it sort of shows our characters in the drama. You've got the bedrock, you've got the sediment, you've got the river. But there's a bunch of other characters I just want to introduce you to. These are people who've helped me a lot and who've contributed to the science that I'm going to present to you now. My mentor, Bill Dietrich, my student collaborators, including Jill in her master's incarnation, and I'll introduce everybody else as they come along in the story. But this is very much a collective effort for which I'm responsible for any errors, omissions, or other stupidity. Okay, so roadmap for the talk. Just, why do we care? Like, I care a lot about sediment. I heart sediment size, but I want you to care too. And I'll go briefly into particular application for understanding the importance of grain size, and that has to do with river incision into bedrock, which is what I did my dissertation research and lots of subsequent research on. But then we'll look up at the hill slope and think about the production of sediment and a little bit about what do we know and what kind of questions remain to be answered, which are many. And then I'll take you to Inyo Creek, California, on the east side of the Sierra Nevada, where we've done an extensive study of a small catchment, trying to characterize the life cycle of the sediment particles that are produced in this watershed. Where are they born? How do they get to the outlet? How are they changed as they go? And we've used field techniques, geochemical techniques, and laboratory experiments, and a lot of cogitation. So we care about sediment size for a whole variety of reasons. The sediments that are delivered to depositional basins tell a story about the environments that they've experienced. It really matters for the carbon removal and the regulation of climate over long time scales. A small particle, the mass distributed in many small particles has much more surface area than the same mass in one large particle. And of course, natural hazards. This is the Montecito debris flow disaster that resulted from a really perfect storm of boulders and mud, right? These two extremes of grain size coming together to make very mobile, very big particles that could destroy houses and upend lives. Okay, but so, from the point of view of rivers, we really care about sediment size because, as I argued to you, they influence everything that goes on. The bed material influences the hydraulic roughness and therefore how deep the flow is for a given discharge, what the flood risk is for a given discharge. It influences how mobile the sediments are, how often they move, how far they move. And that, of course, shapes channels. So the channel morphology depends a lot on the grain size distribution of both the bed load and the suspended load. And then it's not just humans who care, but all the creatures who rely on rivers, the fish here. I look at them and I see them looking back at me and saying, how come you haven't solved this problem of understanding the grain sizes that make my home? And so for them and for everybody else, we want to answer this question. But I came to this question through the problem of river incision into bedrock. This is this astonishing process where rivers cut through solid rock, through whole mountain ranges. And they do it, with water, but they also do it with sediment, as I'll come to. But it's not just the river where the incision matters. It's the river sets the base level for hill slopes. And so as fast as the river cuts, therefore the hill slopes are responding. And And it's really the river network that's like the skeleton that holds the landscape together. And so it's through this process of river incision into bedrock that signals are transmitted from the boundary to the interior of the landscape. And this problem, we thought was a solved problem when I came to it. And this is like a lifetime ago, right? 1996, I was a graduate student, and we had this stream power law. And now I'll just cut to the chase and tell you that this is still the conventional model that people use, and I assert to you that it's wrong. I mean, models are all wrong, right? Some are just more useful than others. The utility of this model is limited because it doesn't include sediment. I jumped ahead. What it does include is discharge, the flow in the river of water, the slope, and the potential energy that you get from the slope, and then some measure of how erodible the rock is. And so there's this expression that says the rate at which you can cut through rock depends on the discharge raised to some power times the slope raised to some power times some quantity that captures the erodibility of the rock. And so I set out to solve this, to calibrate this equation as a graduate student. And how to calibrate it? Well, what people did was they first simplified the matter by assuming the drainage area was a good proxy for discharge. And then, you know, if you like make the heroic assumption that a landscape is all eroding at the same rate, it's in some kind of steady state, and that the rock is about uniformly erodible, you can actually do a little algebra to this expression and rearrange it and solve for slope as a function of area. And this slope area scaling was really fundamental in lots of investigations of landscapes and quantifying landscapes. And here's an example of how you would fit data, channel slope on the vertical axis against drainage area on the horizontal axis. And log space, this power relation is a straight line. And so from that, we can solve for these exponents, the ratio at least of the exponents, and for this K term that captures the rock erodibility. And so there were problems though. If people got into this and compared different places, there wasn't a universal value, even though theory suggested there might be for this ratio of exponents. And it was really difficult to calibrate this erodibility with real rocks in real places. And there's no mechanism here. Okay, this is really, I mean, it's a criticism, but you know, it's a curve fit in a lot of ways. Okay, so my idea was, I'm a civil engineer. I know how to do experiments in the lab. I'm going to do flume experiments. And so I designed these experiments, which I could, control everything. I control the discharge. I could control the slope. I could control the strength of the material by making a weak concrete out of sand and cement. And I could measure the erosion rate, systematically varying all these variables, and solve the stream power equation. There was a problem. I set up a little experiment and I ran water over my weak concrete and nothing happened. And so I thought about it some more. I was like, oh, well, it needs some sand. So I rigged up a way of feeding it sand, and it eroded like crazy. And then I thought some more about it, and I realized, oh, I also need to design this experiment around what's my rate of supply of sediment, what size sediment am I going to use, how does that size and rate relate to the capacity of the discharge and the slope to actually move that sediment. And so it became a much more complicated and more interesting problem. But ultimately, this is all hidden. All these sediment variables were hidden in this black box of these the K's and the M's and the N's. And I decided to scrap that whole thing and start from first principles and ask, what is the role of sediment in driving and participating in river incision into bedrock? Here's an example of a channel in Taiwan, a place that's eroding really fast, and it's just choked with gravel. So sediment has got to matter. And it matters in two fundamental ways. One is that sediment particles are like tools that take the energy or the momentum of the flow and concentrate it in a moment of impact where the sediment collides with the bedrock. However, if you have a whole lot of sediment, it can deposit, even temporarily, on the riverbed and protect the underlying bedrock. So there's this tools effect versus this cover effect. And when you look at bedrock channels in diverse landscapes, you see some that are where the incision rate would be limited. It can't erode fast enough because it doesn't have the tools, or it could be cover limited. What's holding back the erosion rate is the presence of too much cover. So I took this framework, this is sort of a qualitative description, And I made a quantitative theoretical model. So I pictured, particles, bed load particles hopping along, saltating, and they would impart a certain energy on impact, and from established relationships for brittle materials, for how much erosion you get, for a flux of energy. I wrote this expression that the incision rate is a function of three terms: the erosion rate per unit impact, and then the impacts per area per time. So as the particles are hopping along, there's an impact rate. And then there's this third term that captures the cover effect. What's the fraction of the bed that's armored by transient deposits of sediment? And I'm not going to go into a whole lot of detail about this, but grain size is at the core to this. It matters for every one of these terms. And what I did instead of the flume experiment was I rigged up this other kind of experimental setup, which was just a simple tube, a cylindrical mill that I cut discs of rock and bolted them to the bottom of these tubes and filled them with water, and had these motor-driven propellers that would spin the water around, and put rocks of different sizes in there, and then ran it for a certain amount of time and measured the erosion rate by weighing the disc before and after the experiment. And this way I was able to explore the variables one at a time. So here's the influence of the amount of sediment, the sediment supply. These are pictures taken from underneath a glass-bottomed version of one of those abrasion mills. And as the mass of gravel goes from 50 grams to 1,000 grams, we cross through this range of degrees of sediment ability to cover the bed and inhibit incision. Here are some of the erosion rate data: erosion rate on the vertical axis and sediment mass on the horizontal axis. And you can see as the mass of gravel goes up from zero, the erosion rate goes up really rapidly through this Tools effect. But it peaks, it reaches a maximum, and then gradually declines all the way down to zero as the bed gets more and more covered. And I compared this to my model prediction, and the model would predict that the erosion rate goes to zero, but in fact I measured non-zero but very negligible erosion, even at high sediment loadings, presumably because the energy of the particle motion was being transmitted through a thin bed of sediment. But so we're really focused on sediment size here, and I was able to explore sediment size by holding mass constant and varying particle size, and also the number of particles. So one gravel grain would be equal to hundreds of pea gravels, which would be equal to thousands of grains of sand to have the same mass. And here's what the data look like. Now it's erosion rate on the vertical axis against grain size on the horizontal axis, but now on a log scale. These are orders of magnitude variation. And it's starting from the biggest particle on the right. I would put a grain in there and it wouldn't move at all. So I'd have to go to a smaller grain and a smaller grain until I'd get a particle that would move. And those individual particles that were the largest ones that could just barely move caused the most erosion. And as I went to smaller grains and put more of them in there, the erosion rate declined by a couple of orders of magnitude till I got to the point where I was looking at sand that was moving in suspension. And the model predicted no erosion by suspended load, but in fact, I did measure some. And Joel Scheingross, in his PhD at Caltech, came back and did this even more thoroughly and showed that indeed suspended sand could cause some rock erosion. So what does this have to do with topography? Right? Well, if you think about a river and its job in a very simplistic way, the channel slope is very sensitive to grain size and these other variables. And so we could imagine that a river has to be steep enough that at steady state, meaning that the erosion rate matches the rock uplift rate in a tectonically active erosional terrain. The river has to be steep enough, first of all, just to keep the sediment moving. Because if it's not moving, it's not going to be eroding. But it has to be steeper than that because it has to move all the sediment, not just get it moving, but clear through everything. And then it has to be actually a little bit steeper than that to have some bedrock exposed on the riverbed in order to also incise through rock. And so this expression that the slope is a sum of these components, we can sort of map onto this problem the role of grain size and rock strength, discharge, and all the other variables. And this idea is a prediction about how to understand the slopes of actively incising rivers. But the key thing here is that the first term dominates, that the grain size sets the slope, the threshold of motion of a bed load size sets a minimum slope that rivers have to maintain in order to erode through rock. And the implication of this is that that sediment size can set the height of mountains. Because if you take a river slope and you integrate up a river profile, you get the fluvial relief, which dominates the overall relief in mountain systems. So is it possible? This is the hypothesis that the size of what you see on the bed of a river is setting the size of the mountains that are producing that sediment in the first place. Okay, so people tested this idea. Noah Finnegan at UC Santa Cruz found a really neat natural experiment in a place called Boulder Creek. This is a map, the geology map in the upper right corner, where that pink material is granitic and everything else is weak sedimentary rocks. And so the river is flowing in the weak sedimentary rocks the whole way. But as you go downstream, all of a sudden tributaries start bringing in this granitic material, which is much larger. So you get small gravel and mostly sand from the sedimentary rocks, and you get big gravels and cobbles coming off of the granitic. And lo and behold, the slope gets a lot steeper right where those tributaries start delivering this material. The channel also changes its morphology considerably. It becomes a lot wider. It becomes much more covered in sediment. And so what Noah and colleagues did was they applied this theoretical framework of these slope components and found it did a nice job of explaining the patterns that they observed. And even better illustration of the importance of grain size and bed load sediment in river incision is provided by the work of Kristen Cook, who studied a river in Taiwan that was subjected to a big earthquake that created an anticline across the river. This is the Da'an River after the Chi-Chi earthquake in 1999. And the anticline, which you can sort of see in blue in this profile, actually dammed the river and created a pond or a pool behind it that trapped bed load. But it passed the water through and it passed a suspended load through. But for a bunch of years, no bed load was making it to the downstream limb of the anticline. And no erosion of that, even though it was weak mudstone, there was virtually no erosion of that channel downstream until that pool filled with bed load. It took a bunch of years. It took 5 years. And then after it filled, so the flow is going from right to left in this image. And once the bed load started to pass through and go down downstream, it cut this gorge. And there's up to 15 meters of incision over several years as the incision marched headward up this channel. So this is a really dramatic demonstration of the tools effect and the importance of bed load. And Kristen also applied the theoretical framework to use this site to kind of calibrate the model that I proposed, and it worked. She was able to explain these patterns based on measurements of grain size and discharge and inferences of what the flux of sediment was. So this is all an introduction to my story, but it's why I care. And I think we all should be caring about sediment size because of its importance in cutting valleys and in sizing landscapes. But just to summarize, we have theory now, field, lab data, modeling studies that all suggest that riverbed size is central to landscape evolution. And that's through these two effects, the cover effect and the tools effect. And so this leads to a hypothesis that the things that control size are controlling landscapes through size. Okay, so rock type, climate, and tectonics influence landscape evolution through their effects on sediment size and also the amount of bed load sediment versus suspended sediment. So if this is true or whatever, if this is a useful hypothesis for trying to understand how landscapes evolve, we need to know what controls the size of sediments that are produced on hill slopes and supplied to rivers. I say predict in the sense of, we'd like to know in advance before we go to a field site what we would expect to be happening. And also, once they're produced, the particles are born on the hill slopes, but they don't stay the size that they were born. And so we need better understanding of how grain size distributions evolve as particles move through river systems. Okay, so that brings me to my question. What controls the size of sediment supplied by hillslopes to rivers? And we have some basic hypotheses, okay, that they should vary systematically across landscapes. That would be really convenient. And if so, we ought to be able to predict that variation in grain size with knowledge of attributes of landscapes, like the rock, like the climate, like the erosion rate. And then we could model it at the landscape scale. But fundamentally, the overarching hypothesis is this is a solvable problem. Of course, any good hypothesis has a null hypothesis. And here, the null hypotheses are two things. One thing is maybe every hillslope is the same. And there aren't these patterns. And all you got to do is measure it once and you're done. Also could be that every hillslope is unique. Every snowflake we'll never get the patterns. It's way too complicated. And I think this was the implicit assumption when people were like, I'd rather work on something else. But so let's dive into it. Okay, so at the landscape scale, what are the factors we care about? Well, there's the rock type, there's the climate, there's life. Organisms really have a big role to play in creating sediment particles. And tectonics, which drives erosion rates, has got to matter. So we could systematically explore these things one at a time, but they all feed together to create topography. So we could also ask about, are there correlations with sediment size simply but with topographic attributes like slope? Now, there's a lot at play, and so I have a way of trying to talk through the processes that might matter. I mean, we think about a rock parcel, a chunk of deep rock that's deep coming up, being exhumed by erosion of material above it, and it encounters the near surface environment and ultimately the surface. And as it does that, it's transformed from unweathered bedrock to fractured bedrock. And as it gets closer to the surface, it encounters fluids and gases and organisms, and it weathers, it chemically is altered, and it's also altered by physical processes at the surface. And ultimately, it evolves into soil in some landscapes, into saprolite before it gets to the soil, and all that stuff ends up in the river at some point in some state. And a way to think about this is to imagine that you are a parcel of rock, and you want to be bedload, because then you get to participate in the action of cutting through the bedrock to make the valley and matter, right? So what would you do? What would be your strategy to end up as bedload in the river? Well, I have some strategies for you. One is just start out as big as you can be. And then no matter what happens as you pass through this weathering engine in the hillslope, you'll still be big enough to be bedload. Or you might just figure out how to arrive at the surface where weathering is weak, right? And so you're just not going to change that much in the hillslope before you get to the river. Or figure out a way to just move through fast, so that there's not time for weathering to reduce your size that much. Or be really clever and somehow just bypass the weathering engine entirely. So these strategies, if you will, are a way to think about the things that matter. Okay, so if you wanted to start out big, your strategy one, well, how would you do it? What controls the initial size of a movable particle? And there's a lot of things. So in some landscapes, that size distribution is already there. It's sedimentary rocks that are get an inherited class size distribution. Maybe it's the crystal size of the actual minerals that will control how big a space, how far apart the fractures would be. Anyway, the fracture spacing is going to be the thing that kind of determines in a lot of ways how big you are, and that's going to depend on how resistant the rock is to being fractured. It's fracture toughness, and this presumably more tougher rocks are going to make widely spaced fractures and bigger rocks. But so it's lithology and tectonics are maybe the factors that most are at play here. What about strategy two? You want to encounter a weak chemical weathering environment. Well, what controls chemical weathering? It has something to do with the minerals and how soluble they are from rock to rock. Obviously, it has a lot to do with climate and temperature and precipitation. But there's also the process by which rocks are broken up to create fresh mineral surfaces for chemical reactions to happen on. So there's a role for tectonics and physical erosion in driving chemical weathering rates. And so here we have lithology, climate, and tectonics all contributing to chemical weathering and its role in changing particle size. But there's also physical weathering. So at the surface, you're heated by the sun in the morning from one direction and sets up stresses that cause fracturing. Fractures are driven by the formation of ice lenses, something that Dr. Marshall is an expert in, and I'm sure you've heard much about. There's a long list here. I only include some things, but the organisms are involved. There's the role of gravity, and the surface of the Earth can be quite hazardous if you're a particle of rock, right? So we have those things to think about. And then there's what if you wanted to spend a brief time in the weathering engine? Well, how long do particles spend in the weathering engine? What is the residence time and what controls the residence time? Well, we can think of that in two ways. One is there's a size, a volume, and in this case, a thickness per unit area to the zone where weathering occurs. And then there's the rate that material fluxes through there through exhumation and erosion. And they're related. So we have thinner weathering zones and faster erosion. And so weathering, simple calculation will give us many orders of magnitude of residence time for sediment particles in the weathering zone at Earth's surface. And that's going to have a profound impact on sediment size. Okay, but the last clever strategy is the bypassing of the weathering engine. And we see that happen with, for example, tree throw. So tree roots can pull up relatively fresh rock from the base and flip it over on top where it may be relatively safe from effects of water and chemical weathering. But landslides are really the most efficient way to just skip the weathering engine entirely. So there's a lot to think about here. But what if we just wanted to measure it, right? That would be the starting place. And this is my student Molly McLaughlin contemplating this catchment I want to take you to, the Inyo Creek in Eastern California, thinking about, well, how the heck are we going to measure grain size in this landscape? And we could go out with an auger, we could dig soil pits, we could do surface point counts, we could do transects across the surface, we could use cameras, we could just work in the channel. Maybe there's geophysical tools, seismic and so forth, geochemical tools like measuring stuff about the chemicals inside the rock. Maybe there's already existing data and we could just stay at home. Well, I'm going to now show you results from 7 out of these 10 methods. And I've had a whole lot of students tackling different projects, and here are a few of them. Joey Verdian, who's an undergraduate student, went out to ask the question, when you see fractured rock in a cliff, does that tell you what size the particles are going to be that come off that cliff? And so he measured grain size distributions on a whole bunch of talus slopes and different rock types in the Sierra Nevada, and found that indeed the talus size distributions really did match the fracture distributions on the cliff face. And the variations that you see here are driven by rock type, although rock type also has a lot to do with other aspects of where the rocks are in terms of erosion rate and climate. But we found big differences as we went from granites to volcanic rocks to sedimentary rocks. Viviane Merces, walking around on hill slopes in Northern California, noticed that the gophers do the soil digging for you, and had the idea that, well, if we just collected the pits that the gophers dig up and measured the size and abundance of rock fragments, we might be able to test for differences among rock types. And so we collected samples and tested the strength of 3 different rock types near San Francisco. And sure enough, the stronger rocks produce more and larger rock fragments, at least in the ones that the gophers were digging up. But it's a signal that we expected, and it's one line of evidence. Jill in her, or Dr. Marshall in her master's thesis, used data from the Kohala Peninsula in Hawaii, where there's a very strong precipitation gradient. The weather comes from the upper right, and so you have the wettest at the top of the ridge, and as the air goes down the slope, it dries, and you have much drier soils. And sure enough, as we expected, the wetter soils where chemical weathering would be more intense produced much finer grained soils, much fewer rock fragments, smaller rock fragments. And this is just some of Jill's findings. She found this in other places as well, and also did really like 2 or 3 masters, and only one of which was encapsulated in that past slide. So also went to the Sierra Nevada and dug soil pits in places where there was, we were testing the hypothesis that as you move down the hill slope, you would be looking at material that had spent longer in the weathering engine and would be finer grained. And sure enough, fewer rock fragments, and we're looking at the stuff that could be bedload as you go down a ridge, and then also comparing aspect. So the places that were north facing are wetter and had smaller grains. But this is hard work. This is like, is this really worth it? Like, we want to get landscape scale patterns. Isn't there a better way? Well, what if we could just ask the rocks? I mean, some people think they have the story to tell, and we would ask them, like, where were you born? Like, were you up on the ridge? Were you down low? Like, what was it like where you were born? And what about all the other rocks that were born along with you? What's the full size distribution? And then how were you changed on your journey? I mean, if the rocks could tell us, it would save us a lot of effort. Well, they can, except that it takes a huge amount of effort. Here's this question: where in the catchment were you born can be answered with a technique called tracer thermochronometry. And if you're not familiar with this, I'll give you a really short introduction. The idea is that as rocks are exhumed from depth, they're crystals, and those crystals have unstable elements that decay radioactively, right? And down deep, it's warm, and the crystals are kind of loosey-goosey, and the products of radioactive decay escape, helium, for example. But as they get closer and closer to the surface, it gets colder, and you reach a point where the crystals sort of lock up, and they start collecting the helium, and that becomes a kind of clock for how long it takes them to get to wherever you find them. We don't really care about how long that is. Other people do. But for our purposes, what matters is that there's spatial patterns in this thermochronometric age. And so in many places, and in the Sierra Nevada, there's this linear relationship between elevation and chronologic age. And so we can grab a handful of sediments and then do fancy stuff in the lab to be able to figure out what elevation that sediment came from. You also have to go and collect the bedrock data to get this relationship, but we were working in a place where it was already worked out. So this was the PhD dissertation work of Claire Lukens, who's now professor at UC Merced. And we were working in this watershed, the Inyo Creek watershed, which has 2 kilometers of relief and about a 4 square kilometer catchment. So this is a tiny catchment with tremendously steep slopes, but a place where we'll have a very large elevation gradient, and therefore we would expect very large gradients in the things that control sediment size. Okay, so it's much colder up at the high elevation. There's down low is where we have biomass, we have plants, but not up above. The cold causes frost cracking, and overall our hypothesis was that at high elevations we would produce big rocks, and at low elevations we would be seeing small rocks being born. Okay, with simplicity. And so Claire collected these samples at the outlet, and the first data we compared 2 grain sizes. We have a gravel and a mostly sand and pea gravel sample that Greg Stock collected. And what we found was, sure enough, that the gravel was sourced at higher elevations on average. Okay, so this is the graph shows apatite helium age correlated with elevation at the bottom. And so the red, which is the gravel, is more to the right. So it's both older and larger. And this fit with our hypothesis because these lower elevations that were producing smaller particles are warmer, they're soil mantle, they're more vegetated, they're less steep, they're more weathery. And we got this published on the cover of PNAS because it's like the first time somebody had really documented this kind of pattern, which should have been done a long time ago. By the way, in this graph, this cumulative distribution of elevations that the different sizes were produced at, there's a faint gray line, and that's what you'd expect if there was no difference That's the hypsometric curve, how area is distributed. So if every place was producing particles at the same size, it would fall on that gray line. So the next thing we did was to like go there and see what do we actually find. And this was our way of answering this question. What was the size distribution of your siblings, of all the particles that are being produced? And we did this the old-fashioned way. This is the master's thesis work of Jennifer Gidetti and Shireen LeClaire, other students of mine at San Francisco State. And we wanted to test whether this pattern that we saw with the 2 grain sizes, was actually what you find on the surface, throughout this watershed. And we also, so we're testing for a trend in particle size with elevation, and then we want to put in context this thermochronometric. And this is really hard work in a really steep landscape. Like there was no place to pitch a tent. I didn't realize this the first time I went up there. The students were smart and brought hammocks, and I was like, putting my tent on this crazy steep slope. But we were able to sample about half of the elevation gradient and about 2/3 of the area, because it just got too steep and too dangerous to go to the highest elevations. And we did a bunch of those methods, the point counts, the transects, we collected bulk samples, we used photogrammetric techniques. And so here's some of the data. So this is starting at the highest elevation. There are 4 samples from around 2,800 meters. And the top is the cumulative distribution of all the particle sizes that we found on the surface. And below is the median size with elevation. And if you go down 200 meters, it gets a little finer, and you can also see the difference in the topography. You go down another 200 meters, it's substantially finer and safer environment to be in. And all the way down near the bottom, another 200 meters down, it's finer still. And so we can fit a relationship to this, and sure enough, it's a very robust exponential decay in the particle size that we infer is what's being produced at these locations as you move downstream. And so this is consistent with that result from the thermochronometric data, and a nice illustration of the influence of all those factors that we went through. But there's more, and I know I'm probably running out of time. But these particle size distributions were bimodal. Okay, so here's all of the distributions for those samples I just showed you. And if you squint at it, you can kind of see the bimodality, but if you fit a model, so these are 2 normal curves, Gaussian curves, we're fitting the 2 different peaks and also the relative proportion of them. They can all be pretty nicely fit in this bimodal way. And what we found was that there's 2 modes. There's the kind of left-hand fine mode, and that is what varied with elevation. Not only did the mean of the fine mode get finer as you went down in elevation, but also the spread in the distribution got narrower. But the coarse mode didn't vary. And we found that this coarse mode, which was bouldery, was pretty uniform across the whole watershed. And we compared that to measurements of the fracture spacing done both with remote techniques and with really old-fashioned, sending students onto steep, dangerous slopes with stadia rods. And there's no elevation gradient in the fracture spacing. At the same time, there's no gradient in the rock sizes that we measured in this coarse mode. So all of this stuff can be put together. So all that stuff on the left I've already showed you, to a model for what the supply is with elevation. So these are 5 curves for 5 different elevations extrapolated up to the top of the watershed. And what we see is that sand, which on the left side of this plot of model grain sizes, is produced almost entirely at the lower elevations, whereas boulders seem to come from all elevations, and that's there's more at the higher elevations, but they're everywhere. Is boulders. I want you to just hold that for a moment, okay? Because all this time, Claire has been back in the lab working like in a heroic effort to do that thermochronometric measurement in not just 1 or 2 grain sizes, but in a dozen. Okay, so these are Claire's data. It was recently published last year, and there's no data set like this. People have only done like 1 or 2 grain sizes, not every grain size. And there's the signal here. You might not see it, but going from sand on the left, the boulders on the right, these are each point represents an elevation that that sample was born at, okay? So the sand is born at the red elevations, the boulders, over here at the brown elevations. And it's exactly the opposite, okay, to what we measured in the field. The sand appears to come from all elevations, whereas the boulders are mostly just coming from the low elevations. Okay, so just to go back, sand everywhere, boulders only, boulders everywhere, sand only down low. But the thermochron data says sand everywhere, boulders only down low. What's going on? Something ought to give, right? So there's something missing here. Why don't these data agree? We don't have breakdown. Particles, as they travel, up to 2 kilometers in vertical distance, aren't going to stay the same. And in fact, we saw an example of the kind of transport dynamics that would cause the particles to break up. And this was a debris flow. It rained 3 inches in an hour at the nearest rain gauge, and there was a rock fall. What we think it was a kind of a rock avalanche that turned into a debris flow as it gathered material moving down slope, and it ran all the way out into the campground by Mount Whitney. And you can see it really, there's a lot of energy dissipation in this. And so the last part of my talk, and I don't know where we're at. Oh, we're doing okay, maybe. We want to quantify this process and try to understand how it could be that you're getting boulders turned into sand, and that explains our mismatch. So, master's students to the rescue. Okay, well, sorry, I didn't talk about this part of the slide that has the hypothesis, but the hypothesis is that these particles are breaking down in 2 ways. There's fragmentation, which is sort of splitting apart, and then there's attrition, is the jargon of the moment for what used to be called abrasion, this to be the production of tiny, silts and sands that might be worn off the edges. And so that would mean that crystals that are being sampled in Claire's lab work were originally in boulders, but they might show up as sand down at the sampling point or some other size, gravel. Whereas those boulders are just not even, nothing makes it to the sampling point as a boulder unless it only came from right next door. Like if you're a boulder and you're born way up there, you're not going to show up as a boulder at the outlet. So that's the hypothesis. And so we want to know, how do we constrain the rates of particle fragmentation and where? And this is our third question, how have you changed on your journey? Okay, so Gianetta Bianchi took this on, and his experiments involved dropping rocks on a hard concrete floor in the laboratory. And he dropped a lot of rocks, okay? He dropped little rocks that are 10 grams, big rocks that are 1.4 kilograms. He dropped them from 1 meter up to 3 meters. And so we got, a couple orders of magnitude in impact energy. And he dropped them into these buckets with the bottom cut out of them, but to be able to sweep up and measure every single bit of the material that was broken off of these rocks. And he was able to quantify 3 relationships. This first one is, what's the probability on any given drop that the rock is going to fragment? And across the range in impact energies, we get a exponential increase in the probability of fragmentation up to a point where it'll always break, every single drop. The second relationship is the number of fragments. So sometimes only 1 will break off, but other times it'd be 5. And so that also is a nice function of impact energy, a power law, sorry, not exponential. And then he quantified the size distribution of all the fragments that were produced, which collapsed when you compared the child particle to the parent particle, because he knew all those things. So that's great. So we have these relationships, but how do we apply them in the field? Well, to bridge the field, Omid Rabnia, for his master's thesis, used this giant wheel. This is at the Richmond Field Station, which is a UC Berkeley facility, where this wheel was built to study debris flow erosion of bedrock. It was Leslie Shee's dissertation, and other people have used it since. And so Omid filled this thing with cobbles of the rock type, the granodiorite that we're working with in Inyo Creek. and measured every single particle, the mass and the geometry, with a lot of help. And let's see if this is going to work. I just want to give you a feel for what this looks like. Hello, here we go. So this was like scary. But the water was clear when it started. Here, I'll run it one more time just because this is fun. There's very energetic collisions between these rocks, and the water gets turbid like right away. And then what we did was we emptied everything out really carefully, all the water, every particle, and we weighed all the mass, and then put the water back in with the silt to keep track of the evolution of the size distribution, and did this 4 times with these rocks. And so here's some of OMID's data, and the change was small because we didn't run it for a super long time, but we got a huge data set with which to build a model. Okay, so here's a model where we're simulating what happens in that drum, and then trying to scale it to the watershed, which is a big leap, but it hasn't been done before, so it's good to try. And so we use the equations from Jonata's fragmentation drop experiments, and we apply that to making assumptions about the velocity and the particle impact, frequency, and energy. And then this on the lower right is just a graph showing the actual data as the black turns into the red, okay, in this size distribution. And then these are all the possible parameterizations of our model, and we just pick the one that fits best, okay, and we get a pretty nice fit where so the blue compared to the red is somehow getting something right, okay. And now we want to take that and go back to our field data and see, can that explain the mismatch? Okay, so to do that, we need a model for the watershed. So this, we have DEM of the watershed. Every pixel gets a grain size distribution based on the fit to our field data. And then we know the travel distance from every pixel down to the outlet. And so we can take every bit of mass and erode it on the way back. And we can track the crystals that should have been in there. So if you're a crystal and you're in a boulder, in the model, you might be broken into a sand or broken into a piece of gravel, and you end up at the outlet. So here's, and this is the very end. So here is what we get without modeling the breakdown. Okay, so on the left is sand, on the right is boulders. So the model prediction, what's being modeled is just the mixing of all the different sources and all their different size distributions. And the black is the what we would expect with no breakdown, and the blue is what we measure with Claire's thermochronometry. And in both cases, there's a mismatch between the model and the measure. But when we use that tuned breakdown model, well, things get better. Okay, it's not perfect, although the boulder fit is really awesome. When we saw this, we were like, wow, like maybe this really works. The sand, is imperfect, but we did not tune the model to these data. We tuned the model to the lab experiment. Okay, and here's all of them. And now I just want you to squint for a minute, and we'll go back and forth. This is without the breakdown, and so you can see, for example, this is upper left is the smallest sand, lower right is the biggest boulder. Right, you can see that mismatch, and in some cases it's already doing okay, but when we use the model, things get better. Okay, so no breakdown, no breakdown. And so, I won't assert to you that we've solved this problem, but it demonstrates, first of all, that there ought to be a solution to the mismatch between the thermochronometric data, which says that the sand comes from everywhere, and the field measurements will show that you don't see sand being produced at high elevations, and vice versa for the boulders. I mean, one of these to look at is this coarse gravel, the 48 to 64, that's kind of in the middle here. This is what it looks like when we have the breakdown model. And there's a weird kink in the middle here that probably represents something about the catchment and where these sizes come from that's showing up both in our in the thermochron data and in our model data. So we think we're onto something. And so the next steps here are, okay, at the end. But so in summary, we've got a portrait of the life cycle of all the particles in this watershed. You know, it's a fuzzy portrait, but we got it from birth to delivery to the outlet. And we see down valley finding, so on the hill slopes, finding of the hill slope sediment, and that ranges from boulders to sand. And that we also see that the size is controlled in part by the fracture spacing and a shift from physical to chemical weathering. At least that's an interpretation. And this demonstrates the power of this thermochronometric tracing technique to put the rocks back where they started from and understand why they are the way they are. And we've been able to quantify the effect of fragmentation and attrition on sediment grain size distributions. So the next step, and this is what we're working on now, is using cosmogenic radionuclide measurements of beryllium-10 concentration. If you know about this technique, it's like a sunburn. It's actually a supernova burn that the rocks at the surface of the Earth get that you can use to quantify erosion rates. And so combining the thermochron sourcing with the erosion rate data, we can also solve for whether there's an erosion rate gradient. So in our modeling, we assume uniform erosion rate. And then we also have data on the chemical depletion of minerals in these rocks to quantify chemical weathering. So there's a bigger, better story even still to come. So in summary, I assert to you that there is abundant evidence that there are landscape patterns in the size of sediments produced on hill slopes and supplied to rivers. And that size is linked to climate and to rock strength and to erosion rate and to weathering, all those factors. And from the earlier part of the talk, there's abundant evidence and other people's work since then for the influence of sediment grain size on bedrock rivers, their slope, their rate of incision, their channel geometry. And together, this view supports this hypothesis that the way that tectonics, or a key way that tectonics and lithology and climate shape landscapes is through particles, through the particles they produce and the size of those particles and how mobile they are and how they evolve. So there's much more to be done here, and love to talk to you all about it. But that's the end. Oh no, one more slide. I forgot. I wrote a paper that summarizes this and a bunch of other stuff, and it was just published in annual reviews last year. And so if you're curious to know more, and also a guide to the literature of people who have worked on this, I invite you to, it's open access. Take a look at this paper, Grain Size in Landscapes. Okay, thank you.